Chapter 2, we're going to extend our knowledge of derivatives by looking at derivatives of exponential and logarithmic functions, and only a special case of each of those. All right, so we're going to do a brief sort of remind you of exponential and logarithms, and in this class, the only type of exponential function and the only type of logarithmic function that we're going to do derivatives of are the base e, the natural number e. And there's a reason why. It's because that derivative is the easiest. It's also the natural number which it occurs naturally, which means most applications are already set up that way or can be easily converted to the natural number e. All right, so the exponential function in general is any function where I've got a base number that's positive and bigger than 1. Or not greater than 0, positive, greater than 0, and not equal to 1. That's what I'm going to say, not equal to 1. And so it'd be like 2 to the x, 3 to the f. It could be 1/2 to the x, 1/3 to the x. Now again, we're not going to deal with those cases. The one we're going to deal with in this class is the natural number e as the base. When we say the exponential function, when things grow exponentially or decline exponentially, it's the natural number e that's the base of those kinds of functions. And so that's the one we're going to deal with, and it actually is the one that the derivative is a lot easier, so that's why it's the only case we're going to deal with. All right, so the exponential function we're going to deal with in this class is e to the x. So e is the base, so it's the natural number e, which is that 2.7, that decimal that goes on for forever. All right, and so e is an irrational number like pi, and that's what the base number is, and then the exponent is the variable. I can plug anything I want into that, positive, negative, decimals, fractions, rational, irrational. Its domain is all real numbers. It's also never 0 or negative, so that's again important. E to the x can never be 0, and e to the x is always positive, greater than 0. All right, never negative. You can't. It doesn't matter what you plug in, because if I plug in a negative number like e to the negative 1, well, what that really means is 1 over e to the first, or e to the negative 2. That really means 1 over e squared. All right, so when I plug negative numbers out, it just makes it a fraction. All right, so again, it is never 0. There's nothing I can plug in to make it 0, and then it is always positive, which means its range is 0 to infinity, positive numbers. It does have an asymptote. All right, the x-axis is the line y equals 0, and if you graph it, so the graph of this function, you graphed it out on your calculator, it only lands in the first and second quadrant. All right, it's always above the x-axis, right? That's the line y equals 0. It's its asymptote. All right, it goes to the line 0, 1, right? If I plug 0 in, right, e to the 0 is 1. Right, anything to the 0 power is 1. And then again, it's growing really fast when I plug big numbers in, and when I plug negative numbers in, it's fractions, and so those numbers are getting smaller and smaller, and again, it approaches as x goes to negative infinity, the y values, the function values approach 0. And so it does have asymptotic behavior. It approaches 0, but never ever gets to 0. Its limit would be, as x goes to negative infinity, would be 0. And so that's the e to the x function. It's always increasing. It's always positive and never 0. Right? Always moving up. Its slopes, therefore, would always be positive. Its slopes, which is its derivative, all right, which we'll get into in the next section. All right, so there's the natural number e as the base exponential growth function. To go with that, all right, we're going to look at the logarithmic function. And again, we're going to get to the logarithmic function base e. Now, and again, I'm going to hit this briefly, but the whole purpose of a log function is to solve for the exponent, and the exponent is to be the inverse of the exponential. Okay, you should have talked about this somewhere in an algebra class before. All right, so I've got this exponential function, a to the x equals b. Well, how do I solve for x? Well, there is no algebraic way. All right, we cannot solve for the x. We know the x exists, right, because x exists for all numbers from negative infinity to positive infinity. But there's no algebraic way to do it. And so what they did, well, they created a function that allows us to solve for it because we know it exists, and then that function has rules. All right, they called it the logarithmic function. There's probably a reason why. It probably has something to do with Latin or whatever. But we call it a log function way back when. And so the design of this is because there's no algebraic way to solve it, they created a function that solves for that exponent. All right? And so log base A of b equals x means x is the exponent on base A that gives the value b out. And so a couple simple examples here. Log base 5 of 25 equals x. And so what that means is 5 raised to the x equals 25. I know that exists. Actually, I could figure that out in my head. All right, the x has to be 2. 2 equals the log base 5 of 25. That's the exponent on 5. All right, 2 is the exponent on 5 that will give out the value 25. All right, my second example is a little trickier than that because it's going to lead us into the natural number. So log base e of 120 equals x. And so again, using that same rule of thumb, this is e raised to the x gives me out 120. Now this one I can't solve in my head. Right? I can't do it. But there's a program on your calculator that allows you to. And so what we'd have to do is we have to figure out the x value. And what it turns out to be is when we have log base e of a number, that's the log of the natural number e. Well, since this one we're going to deal with and it tends to occur in nature, we give it its own notation. That's the ln, which your calculator can find. Your calculator, you have a natural log key on your calculator. If you type in on your calculator, you'll find it there. All right, it's under the log key, under the log, it's ln. If you type in ln of 120 into your calculator, hit enter. It's an ugly number. Because, again, e is an irrational number. It comes out 4.78749. That is the answer. That's the exponent that I have to put on e to get out 120. All right, so e raised to the 4.78749, roughly, comes out 120. All right, that's the natural number e. And again, so the natural log base e, is the one we're going to deal with in this class. So to formalize that, all right, so if I have a log base e, we give it its own name since this is one that occurs in nature and that we use all the time in applications. So log base e is the natural log, all right, ln of x, the natural log, and that's true if this equation's true. All right, where the x value, all right, is the number that comes out when I take the e raised to the y value. Again, x values have to be positive, all right, and the base e is the part we're looking at. All right, so the graph of the natural log, y equals ln of x. It's the inverse of the y equals e to the x function. It's its inverse. And so if you remember inverses at all from your algebra classes, inverses are reflected over that y equals x line. So remember, the e to the x function, if I graph it up here, and I'll graph it up in a different color. Graph it in red, remember, was the expression like this. All right, that's the e to the x. Well, the natural log is the flip of that. Remember, to be an inverse, we flip the x and the y. All right, which means we get y equals the natural log of x is true if e to the y equals x. And so we flip x and y. And so what we do is, we get this expression down here. We flip x and y, so the point 0, 1 becomes 1, 0. Instead of approaching the y equals 0, we approach the x equals 0. And so this is going to come down, and it's going to shoot down here to negative infinity. All right, as I get closer and closer to the x being 0, it's going to go down to negative infinity. And then on this side, it's going to grow slowly. And so the blue line here is my natural log function. All right, the natural log function, its domain has to be positive. I can't plug if you try to plug a negative number in to the natural log, it'll give you an error. Or if you try to plug 0 in, it'll give you an error. However, its range is all real numbers, is everything. All right, I get everything out from negative infinity. This is growing forever. It's growing slow, but it is shooting up here to positive infinity. So I get every value out, but I can only plug positive values in. All right, so, and it is an increasing function. You'll notice it's increasing everywhere, so the slopes are positive everywhere. Slopes are positive. Everywhere here I've got positive slopes. All right, so it's increasing everywhere. And so that's sort of the natural log. And we can always convert to it. Now, our examples will always have them built in. But in case you ever run into an example that's not in the natural log form, we can always use what's called the change base form. Alright, so the change of base form is if I have a log base A of b. Alright, so this is sort of the value I want to find. Log base A of b. Well, in order to get that, you can change it to either the log base 10 or the natural log. Since in this class we're going to deal with the natural log, I'm going to convert to the natural log. And so what this is, the change of base formula is I take the natural log of the inside term divided by the natural log of the base term. So try that out on one we did earlier. Remember, the log base 5 of 25, I know that's 2. But use the change of base formula. Take the natural log of 25, type it into your calculator. Take the natural log of 5, type it into your calculator. It should give you 2 out as your answer. And so we can always convert to the base e. Alright, we'll stop there. We'll pick up properties of logarithms in the next video.